Section 3.6 is called the chain rule, and it's all about you. It's all about you, right? As a teenager, it's all about you. Well, in Section 3.6, it's all about you also. Let's first review composite functions that we looked at last year. If we have the sine of x squared plus 1, we have an inside function and an outside function. Let me show that. If the outside function's f and the inside function is g, I always start with the inside function here, and that would be x squared plus 1. And then you just ask yourself, what's that inside of? And it's inside sine of the input. And here the input is x squared plus 1. All right, on the second guy, we would say the outside function would be something to the fourth power, and the inside function is x to the third plus x. All right, let's move on. We're going to be using that in this section a lot. All right, we're going to take the derivative of a composite. So we're going to start with fu. Yes, I really said that. We're going to take the derivative of a function that has an inside function. So here we have, we're going to take the derivative with respect to u would be 3u to the second power. All right. Now, if u is an actual function, we're going to have to do a little bit of extra work here. If it's not simply a variable, if it's an actual function like we saw on the previous slide, we're going to have to do a little extra work. And that little extra work is, if we need to find the derivative of with respect to x, where u is composed of x, and we're going to look at some examples here in a second. What we're going to do is we're going to throw that exponent out front. The base is still going to stay the same. It'll reduce the exponent by 1. But then you're going to tack on the derivative of the inside function. This is the derivative of the inside function. You're going to add a link, like a chain link. You're going to add another link in a chain. That's why it's called the chain rule, and it is the derivative of the inside function. So the derivative would be 3 times the original function squared, the original inside function squared, times f prime of x. All right, let me show you why this works out. All right, there's quite a bit on this page. Let's suppose we have a function, and it has an inside and an outside function. See, u is the inside function. That was our g of x on that first slide. And f is the outside function. Okay, so u is our inside function. So we really have f of g of x, just like I did on the first slide. Well, our goal is to find the derivative of y with respect to its variable, which is x, not u. All right, because like we saw on that first slide, we had like the sine of x squared plus 1. There was no u in the picture. There was an inside function, and we called it g of x. So let me show you how this works. We're going to take the derivative of y with respect to u. So you're going to take the function f and take its derivative where you think of that inside function as the variable. Then you're going to take that inside function and find its derivative with respect to x. Our goal is to get the derivative of y with respect to x. Now I want to show you a little bit of algebra here. dy du. And then if we do unit analysis and multiply by du over dx, watch what happens. The du's cross cancel. And when you multiply straight across, you get dy on top and dx on the bottom, which is exactly what we want. So this is called the chain rule. Right here, this is the chain. This is the derivative of the inside function, u, where x is your variable. And then the first part is the derivative of the outside function, where the inside function is your variable. You just think of that inside function as u. All right, remember, it's all about u. Okay, let's move on. All right, so here's a nice example. We got an inside function that's pretty obvious here. the inside function is t squared plus 1. So let's find du dt. The derivative of the inside function with respect to t, which is the independent variable here, is 2t. All right, now, the derivative of the outside function, of course, is negative sign. Negative sign. So the answer here for velocity is going to be the derivative of position, and we get negative sign of t squared plus 1, because remember, u stays the same here. It's kind of like when we do the power rule and we say the base stays the same. We are going to keep that the same. Derivative of the outside function, where u is your variable, and then we tack on your chain, which is your du with respect to t here, and we get 2t. All right, so probably the way they would write this answer on the AP exam would be negative 2t, probably put that out front, sine of t squared plus 1. Now to do the acceleration, you'd have to do the product rule because this is a product. So let me go ahead and do that. It would be the first times the derivative of the second. Okay, here's the derivative of the second. I'm going to put a big bracket here. I'm going to change color. It's going to be cosine of t squared plus 1. Now don't forget to tack on the derivative of the inside function. So another 2t goes there, plus the derivative of the first times the second, unchanged. So there's the product rule. So if you need to pause the video here and really study what I just did, it would be really good to do that. And pay attention to how I tacked down the derivative of the inside function whenever I was taking the derivative of a composite function. All right, so here's another one. We're going to take the derivative of sine x squared plus x and find dy dx. So the outside function is sine, so you start there. You start from the outside and you say, hey, the derivative of sine is cosine, and what's inside just stays the same. That's your u. And we're going to tack on the derivative of the inside function, 2x plus 1. End of story. Or you might write it as 2x plus 1. You do need parentheses, folks, because if you're going to simplify or multiply this out, you have to do the distributive property. All right, let's move on. Here's a problem that has 3 lengths. Please pay close attention to this one because we're going to take the derivative of sine to the 4th. Well, how do you do that? Well, first thing you do is think of it this way. Something is being raised to the 4th power, and that something is an inside function. And inside that function is yet another function. So we have 3 links here. So let me show you how this works. To take the derivative, you throw the 4 out front, the base stays the same, the exponent goes down to 1. Now, I said the base stays the same. Excuse me. So now I've put the base sine of 3x in there. Now I have to tack on the derivative of that green portion, sine 3x. And the derivative of sine is cosine, where the inside stays the same. However, we have to take the derivative of 3x and add a link here, because that's an inside function, and we were taking the derivative of sine 3x. So it's cosine 3x times 3. So the final answer would be 12. Sine to the 3rd, 3x, cosine 3x. Now notice how I move that 3 back above right here. I move that instead of an exponent up there. This is how you think of sine to the 4th. A lot of students think about sine squared this way, which is exactly right. You need to think of squared, like sine squared x. That's a chain rule question. All right, let's move on. All right, the power chain rule simply says you throw that exponent out front, the base stays the same, reduce the exponent by 1, and then tack on the derivative of that u function. So that's the power chain rule. I've already gone over that and been using it, but there it is in print. All right, parametric derivatives. Oh my goodness, you thought you were almost done, and here we are, parametric derivatives. Here we have a circle. This would be x squared plus y squared equals 1 squared, or parametrically, you could write it this way. So as time goes along, remember, you start somewhere when time goes along. I believe you start right up here at time 0. And no, I'm sorry, you would start over here at time 0, and then it actually circles around this way as time goes along. Well, how would you find the slope of the tangent line, like over here, for example? Well, you'd have to know at what time that is, and then you could figure it out. So the way you're going to approach this to find dy dx is you're going to take the derivative of y, dy dt, where t is your variable, of course, sine t. You take that derivative, and then you're going to multiply by the reciprocal of the dx dt. Why would we do the reciprocal? Well, I want you to notice, this is called Leibniz notation. Dy dt is Leibniz notation. What's really cool about this is not only that it was founded by a guy with a cool name, Leibniz, but that you can think of these things as changes or deltas or actual numbers. dt's can cancel, leaving dy over dx, which is exactly what we're looking for. So let's find dy dt. The derivative of sine t is cosine t. And then we're going to multiply by the reciprocal of dx dt. Now dx dt, I guess I could write it up here, is negative sine t. So we multiply by that reciprocal, negative sine t flipped over. Now you multiply fractions straight across, and cosine over sine, if you recall, is cotangent. So that would be the answer for dy dx. The derivative of the y component with respect to the x component. But look at this, it is actually in terms of time. So if they put at time equals pi over 2, you would put pi over 2 in there, and that'd be at the top here, by the way. And you would find the negative cotangent of pi over 2, all right, which would be 0, negative 0. And we do see that the horizontal is a 0 after 90 degrees of rotation, or pi over 2 in time. See, it's all related. All these radians and things are related to the unit circle and parametric equations also. All right, so this is how you find the derivative parametrically. All right, so what's key here in 3.6? You need to learn to spot inside functions, and the chain rule should come to mind. You are always going to tack on the derivative of that inside function. So here I see something being raised to the 5th power, and that something is a function unto itself. So in this example, y prime would be, you throw the 5 out front, the base stays the same at x squared minus 1. The exponent goes down by 1, but then you tack on the derivative of the inside function, which would be 2x. So the final answer here would be 10, parenthesis, 10x, x squared minus 1, all to the 4th power. All right, good luck on your homework. This takes a little bit of practice. It's really just a nuts and bolts kind of section where you just have to learn how to do it. You don't have to understand too much of what's going on. Just have to learn how to do it correctly and apply that chain rule. And also, of course, those parametric derivatives that will be on the quiz, the test, as well as the AP test. All right, good luck.